Welcome, everyone, to DenverScript for August of 2023. I'm your MC, Marlena Baker, and I'll be kicking us off tonight. Welcome. First of all, a quick note on our code of conduct. DenverScript is dedicated to providing a harassment-free community for everyone. And if you're violating this, you may be sanctioned or even expelled. If you have any issues while you're here at the meetup or in the community in general, you can talk to one of the organizers. That would be me, Will back there, CJ right there, and Cass in the back. But basically what we would like from all of you is to be kind. Let's be a great community for each other. So do not talk over the organizers or the speakers. And during the Q&A, ask constructive questions. Don't try to prove a point or get a gotcha in on the speaker, because nobody enjoys that. I'd also like to mention that we are live at DenverScript Meetup on YouTube. This meetup will be live streaming. What that means is, because we'll be live streaming all of the meetups, if you can't make it, you can always join the live stream. If you want to revisit a talk, there will be a recording on YouTube, which is awesome. It also means that when you're asking questions today, please be sure to get a mic from one of us, me today, so everybody in the room and online can hear your question. I want to thank our sponsors. Code Talent is sponsoring this lovely space, as well as the beer and seltzer. And our lovely Cass has brought the food today. Her Venmo is at Cassandra T, and it is also on the food table if this slide goes away and you don't remember it. Donations are very much appreciated until we get a sponsor, which we're looking for sponsors. So if you work for a company that would love access to a lot of really awesome JavaScript talent, you should let them know about this meetup, because look at this room. It's packed. It's packed. We're also always looking for speakers. You can submit your talk at DenverScript.com, at which point an organizer will reach out to you about getting you scheduled for one of the meetups. And public speaking is a great way to get yourself out there in the community as well. And now I'm going to hand it over to Cass for our JavaScript news.
There's a soft booth over here, and if you're looking for a seat, we're also more than welcome to come steal one of these if we move our stuff.
All right. Hello. Welcome, y'all. You can find my bulleted list of news on DenverScript.com. There's a news tab there. But I'm going to just do a overview for y'all. And then hopefully you can check out the website if you're wanting more information on anything. Or you can just Google it yourself. I mean, all this stuff is out there. So we'll start off with just some things that happened over the last few weeks. One of those things was that there were some React Jam winners. So React Jam is like a online event where React developers build a game, and they have like 10 days. It needs to be under like 10 megabytes, and then basically people play, and the people, there's no like judges as far as I understand. If your game gets the most plays, as in people are clicking in and spending time playing your game, then you win. Pretty cool. So if you haven't heard of that, maybe put it on your calendar for next year, because that'd be cool if one of you all won next year. Speaking of games, JS13K Games, which I had never heard of, is a competition that just went live. And you actually have, I think, until sometime in September to submit a game. The trick here is it needs to be under 13 kilobytes. So a little bit of a constraint, and you gotta use JavaScript and HTML. I don't know if you can use anything special on top of that or abstract anything away, but please look into it, because again, it would be really sick if one of you won, or at least competed. So please tweet at us if you end up competing, because I think that'd be interesting to hear about. Apparently, Google is working on a new IDE. I don't know much about it, but it's browser-based, and it's got an AI, which you're probably not surprised to hear. So that could be cool when it comes out. It could also just be nothing, but put it on the radar. There's a library that's actually been around for quite a while, but it has recently joined the GitHub Accelerator, and this is called HTMX. Pretty cool. Basically, You can use it to make your web pages interactive more easily. Let's say you don't want to write vanilla JavaScript or you don't want to use React. Maybe this will help you. I don't know much about it, but check it out. A couple of other things I want to call out. There are some conferences coming up, and there are some conferences coming up way out that are like inviting people to speak. And you all would probably be lovely speakers. One of those is, let's see, Developer Week. I don't know much about this, but call for proposals is open, so please check that out if you're interested. Getting Denver representation is always awesome for that type of thing. A couple of other conferences that you might be interested in: JavaScript and Friends, Utah.js, Borderless.js, TS Congress, Underground.js, Redwood.js, and JS Game Dev Summit. And then I also saw that GitHub Universe is 30% off right now. If you're interested in paying $1,000 to go to a conference, that's probably, today is the day to buy that ticket. Some releases. So Fresh 1.4 is out, and I really was hoping that I didn't get the news, like I wasn't assigned to news or picked to do the news when there was tech involving Dino or Deno or Dino or whatever the heck it's called, because I don't know what it's called. Dino? All right, we're sold. It's Dino. But check out the docs. They were boasting ahead of time compilation and support for layout files. And they had layout, but it just couldn't be like nested or something. So dig into that. Electron has a major release, so dig into some of that. They're ending support for an older version, so if you're using an older version, maybe check that out. Astro has a new release, and I like this because you can now keep the state of DOM elements from a previous page as you transition to a new page with a new directive. You could probably figure out a way around this before, but it's nice and easy now. Angular's got a new release, Playwright's got a new release, Node's got a security release. All of these are, of course, interesting. Please check them out on the website if you're interested in reading more. I have also included on the website a couple of articles that were released this last few weeks. One of them about Three.js, so if you're interested in like making like 3D modeling or anything like that, check that out. There's a new syntax podcast on 6 or so new approved and proposed JS APIs. Check that out, seemed interesting. There's a new Next feature called React Server Actions, which could also be useful. And then I do want to spend a moment to call out that a lot of us probably have friends who've been laid off recently. We have friends who are newer developers trying to break into the scene and are struggling. So I just want to say, as a news item, I encourage everyone to befriend one another, maybe do some networking with one another. If you hear about an opening in your job, post it. There's like Denver Tech Talk, a Slack, there's Colorado Tech Community, a Discord. It would be awesome to get one of your like close DenverScript friends a job. So just calling that out. And yeah, that's it for the news. I'll pass it back to Marlena.
I have a question.
Yeah.
What is this website you keep speaking of?
DenverScript.com.
DenverScript.com. All of the links for everything she just talked about is there.
Thank you for asking.
Thank you, Cass. And here's a look at DenverScript.com. I don't think you'll miss it when you get there. And now I would like to hand it over to Mr. Coberly to talk about eslint.
Check, check, check.
Hey everyone! My name is Kyle Coberly. I am a software engineering coach, and I'm going to talk about eslint today. Can you make some noise if you ever were one of my students or one of my employees? All right, so a few people. All right, that's who I am. All right, everybody. So eslint is a linting tool. Linting tools are about ensuring consistent code standards in a project. eslint was not the first JavaScript linting tool. That was probably, I think JS Hint was the first one, maybe JS Lint. And then a guy worked on JS Lint for a while, but neither of those were extendable with your own rules. So he came up with eslint. We can add our own rules to eslint, and that's the thing. Another cool trivia piece, linting as a concept came from Douglas Crockford, the guy who wrote JavaScript, The Good Parts, and it was like getting the lint off of your clothes. All right, so the way that you've historically configured your eslint stuff for your projects was with this format called eslintRC. It's this one object that you could do in a variety of different formats. You can do it in YAML, you can do it in JSON. It is cryptic as hell. I've been using eslint now for almost the entire 10 years, and I still need to look this up every time. Doesn't really make any sense to me. And maybe the thing that bugs me the most about this is you'll notice that when you're doing things like plugins, it's just strings. And so you have to know that you have that installed in your project already. You don't get an error or anything until you're like actually using it. So they last year came out with a new format for their config called flat config. Ooh, ah. So flat config, way easier. I made a squee sound thing about how much easier this is going to be to teach. So instead of before, when we were exporting this like one confusing object, the flat config is an array of config objects. Each one of them maps to a subset of files, and each one of them can have their own configuration, their own parsers, their own whatever. It's also updated in a lot of other ways, such as using ESM instead of CommonJS. So specifically, differences that you'll find between the eslintRC format and the flat config is that instead of all of the different formats that we had before, which were .eslintRC, which was JSON, .eslintRC.json, which was the same thing, .eslintRC.yaml, and like I think 2 or 3 other ones also. All of it is .eslint.config.js. That's it. Instead of that complex top-level object, you're exporting an array of config objects. Instead of having string-based plugins, you just use the damn plugins. You import them in, and you can do everything that you can do with JavaScript in that. You can spread objects and arrays. You can use just parts of it. And so you don't have to learn a specific ESLint specific way of configuring this. You can use the JavaScript knowledge you already know. Instead of forcing you to use CommonJS for your config, it's all ESM based. So you don't, I feel like we've kind of been in this process of transitioning the whole like Node ecosystem into the ESM world. And this was like probably the most heartening one for me. As otherwise, you have to do all these special exceptions for the different things in your project that do or don't support ESM. And then all those cool configurable rules and like this really rich plugin ecosystem for React and Storybook and Vue and all these different tools, exactly the same, baby. And that is my quick and dirty intro to flat config in ESM. Thank you very much.
Any questions? Here, swap me.
What is your favorite eslint plugin and why?
Ooh, that's a good question. My favorite eslint plugin, probably the TypeScript one. I mean, that's kind of cheating a little bit. Like, really, I don't use any eslint plugins that I don't have to use, but I use that one and like import and storybook and React and TypeScript, and I think that's probably about it. Good question. Oh. What else? What else you want to know about eslint? Yeah.
I'm just curious, what exactly is ESM? It's just, I'm
Oh,
fairly
sure.
new to JavaScript.
Absolutely, happy. So check this out. You'll notice in the RC format, there's this module.exports. If you've done any like Node stuff before, you've seen that and require. That's a format called CommonJS. So when Node came out, JavaScript didn't have a module system. And so Ryan Dahl was like, all right, well, I need a way to isolate these different things. You can't just have everything in the global scope like we did with JavaScript at the time. And so he came up with CommonJS, which is that require module exports format. This was super influential and led to ESM, which is this import-export syntax. That's actually part of the language spec itself now. So if you've done anything on the front end, you've probably seen that before. And we're in probably the most like awkward puberty era of JavaScript, where we're right in between these two formats. And I think this is going to not be an issue in like 2 years. But we still got kind of a bumpy road ahead of us coordinating between the two formats. Good question. What else? Do one more. Jonathan.
Along those same lines of fun, what's the most sort of bike-shedded ESLint rule you've seen?
Oh, that's a good one. Man, I actually end up disabling a lot of stuff. Like I use Airbnb as like kind of my baseline, and then I disable like 24 things in it. It's just like, and actually I got this piece of advice once. If you find yourself like doing a bunch of one-off things for any particular ES rule, just disable it. And I think one of the reasons that people didn't do that for a long time is in the old RC config, it was actually really difficult to figure out where you were supposed to do that. Because you could do rules at the top level, and then you also had an overrides, and then you could also do stuff with the plugins themselves. And all this gets a lot easier with the flat config format. But to more directly answer your question, semis. I don't care that much about them anymore, especially like since Prettier just kind of takes care of it for you. But I don't care for them, never have. And tabs versus spaces. That's another thing that like with Prettier and ESLint, I write it however I want to, and then I don't think about it that much. But tabs are an accessibility issue, so I win. All right, thank you very much.
Hello? All right, attention to the front, please. I'd like to introduce Mikey Sleevi, giving a talk on promises there and back again.
Check, check. Cool. All right. So I have a loose Hobbit structure for this because there's a little bit of a meandering path to get through this. This is a fairly rough talk. I did not have as much time to put it together as I wanted to. There was a lot of incidents at work last week, so took up all my time. But the goal of this talk is really to talk about the glue of how promises work. We're going to talk about a lot of low-level features and a lot of really in-depth stuff. And I'm going to take you all the way down and bring you all the way back up and kind of stitch together some pieces. And hopefully, after the end of this, you can kind of take it and learn those pieces on your own. So I wanted to start with a survey. Kind of raise your hand if you know what's going on here. So we're going to start out with we'll start out with who knows what Node.js is? Okay, a lot of people. Who knows what a promise is? Great. What about an abstract syntax tree? Okay, we're losing some. Bytecode? Okay, we got some back actually. An event loop? We got a lot back. Epoll. Okay, we're down to like 3 people. File descriptors. We got some back. There's like 8 people now. What about a level trigger? Okay, we got nobody. All right, so we've hit exactly where I wanted to get. No one. So I start all my talks with weird abstract quotes, which this one is any fool can know. The point is to understand. So I chose to lean on epistemology, which is kind of a branch of philosophy concerned with knowledge. And according to that, there's 3 forms of knowledge. There's those being knowing that, those knowing how, and knowing by acquaintance. So I've chose to really focus on 2 throughout this talk. Actually, really in particular 1, kind of talking about how 1 is not sufficient in our industry. So there's procedural knowledge and there's descriptive knowledge. There's knowing that and knowing how. The easiest way to think about the difference between these 2 is that descriptive knowledge is my test-taking routine. I know something, I recite it, and I put it on the test to get good grades. An example of this is I know that polymorphism means having many forms, and I know that overloading is when 2 or more methods in the same class have the same method name but different parameters. And that overriding is when 2 method names have the same method name and parameters. Whereas procedural is my knowing how things work. I know that overloading exists as a means of ad hoc polymorphism, and that overriding exists as a means of subtyped polymorphism, and that overridden methods are executed by a means of upcasting and late binding, or devirtualization at compile time, in order to determine which method in the inheritance hierarchy to utilize. Lots of big words there. I promise it won't be like that throughout the whole talk. But what I'm trying to say is down with abstractions. The idea of how versus what is explored by Richard Feynman in a series of papers. One quote I particularly enjoy is given here. What this is saying is that we cannot solely rely on reciting information as if we are taking tests. We must be able to digest it and make this information our own. We should seek thorough understanding of ideas. And when Feynman says the person who says they know what they think but cannot express it usually does not know what they think. To kind of dive more into more of my view of this, I got this quote from me, which is, "You'll find more value." Maybe. Are we good? Seems good. You'll find more value in chasing roots of things you cannot express than you will in finding more things to not be able to express. So chasing roots is the motivation behind choosing what we learn. When we elect to desire something and are forced to make that decision between the variety of things that we have the option to hold important, we should chase those roots. We should seek to understand how. We should chase the roots of things and find more things that we don't understand. As an example, the Java programmer that chooses to learn Kotlin when they don't understand the JVM does not gain any knowledge of the JVM in this pursuit. Instead, they learn more of the that without growing their knowledge of the how. We should prioritize building our base, or as I like to say, learning Latin. It's a reference to an old aphorism, so that we can understand the how of it all. So when we decide what to desire, we should focus on the how. That seems a lot more enticing. So enough with the philosophy. Let's get into some actual JavaScript here. So we're starting with a simple program here, and this is going to be the main focus of the talk. We are doing a really simple promise here. We return a fetch. It has a then, and it has a catch. We just say promise resolved, promise failed, and this is a website that I own that has a picture on it. And then we just run the promise at the end. Nothing crazy going on here. The things I want to highlight are the fetch, which is effectively the promise that we're executing. We're making a network request. And then we have callbacks for the then and the catch. So starting out, if we want to understand what a promise is, what that JavaScript program is doing, we got to start by talking about what is Node.js. And so Node.js, there's a cross-platform open source server environment that runs on a bunch of different systems. It's primarily a back-end JavaScript environment. JavaScript used to be all front-end. Ryan Dahl, as Kyle mentioned, kind of brought us the back-end side of things. And we have this V8 JavaScript engine here that executes JavaScript code. So we're going to explore this a little bit more here, and I'm going to start out with this crazy diagram. This is a lot. This is a lot to take in. Really what we got going on here is we have a JavaScript file that's going through this weird thing here. There's a rocket ship, there's a tree, there's my version of what is bytecode, there's a fan, and then we got the next thing, which is a loop. We got some queues, we got some heaps, we got this magic file thing down here, and then we talk about some interrupts. So really what we're going to be doing is we're going to be using this as the exploration of our journey here. And we're going to be focusing on subsets of this diagram. We can't learn the whole thing in 50 minutes, unfortunately, but we're going to focus up as much as we can here. So let's talk about a promise before we get into that. So it's a proxy value. We don't know what's going to happen. It's an asynchronous thing. And we have these callbacks that are executed like synchronous methods. They have the success, they have a failure, and we don't know when it's going to return, but we do know it's going to return at some point in the future, hopefully, or error. That's a lot of words, so let's break it down into some scary C++ code. So this is our scary C++ code. This is direct from the V8 source code, kind of the definition of a promise. We have something that's an object that has this resolver that does this resolve, reject, catch, then. If you break it down, this really isn't too much different than what we think of as a normal JavaScript promise. We have a resolve and a reject, which we're all familiar with. And then we have catch and then execution methods on it. We have two different ones. We have a handler, and then we have onFulfilled and onRejected. So we have one that's kind of broken out into pieces and one that is just a generic handler. But we're still seeing the same structure that we see in our JavaScript promise. V8 has an interesting definition of what a promise is. I chose to pull this straight from their blog because breaking down my promise was a little bit more complicated than theirs. But from V8's perspective, they have a variety of things going on here. They have an implicit promise around this await. They create a promise, and then they resolve this promise V. So we create an implicit promise, and then we resolve a promise that's V with this await. The implicit promise represents the whole asynchronous function. The normal resolve is just our await command going. And then we have this throwaway. The throwaway is for our handlers. So we create a promise. Once we perform our promise that is resolved, we have a resolved and an error, kind of how we do in our V8 code. And then we have this suspend, which is magic. We don't need to talk about that. That's V8's optimization. But at the end, we resolve the overall promise, which represents our async function. So let's start by talking about what a promise's journey is going to look like in the context of our original diagram. So we got a bunch of things grayed out. These grayed out pieces you can mostly ignore. What's going on here is we have JavaScript moving through that tree into that rocket. We stop at the bytecode. We're not going to go through the rest of that loop. It's very complicated. We jump straight to the event loop. We kind of iterate through some things down there. We go to these file descriptor things down here, which we'll talk about. And then we kind of come back and around all the way back up to JavaScript land. So with that, we're going to start with our first Hobbit reference, JavaScript down into the caverns of V8. V8 is this compilation and execution and garbage collection, and it's really the thing that runs JavaScript. There's a lot of different versions of what V8 does, but V8 for the most part is the one baked into Node.js. Firefox uses something called SpiderCore or SpiderMonkey now. There was Edge using shock record for a long time, but I think they've given up and gone on to Chromium. So yeah, so we got V8. But what does this really mean, this big, long thing? There's two things we can break it down into. Compiles and executes JavaScript source code. Compilation pipeline. Handles memory allocation for objects and garbage collects it when it doesn't need it. This is a garbage collector. We don't really need to be concerned about that with this talk. We're not super interested in how the garbage collector functions for a particular promise. So we're just going to talk about the compilation pipeline. And really, we're only interested in a subsection of the original image that we were talking about here. So when we break down the compilation pipeline, we have three major components: parsing, ignition and bytecode, and turbofan. We're not going to talk about turbofan. It's a real compiler, and it's very complicated. So we're just going to stick with the ignition and bytecode pieces. Parsing has to happen regardless. Parsing is basically building an AST. We need to build something a computer can read from our JavaScript code. So we're making sure it conforms to the rules of grammar. This is the thing you run into immediately once JavaScript panics and says, I don't know what this thing is, or this variable is misnamed and misused. So we're trying to make sure it conforms to a formal grammar, but really what we're doing is we're trying to build an abstract syntax tree. So the source text is processed, V8 parses that, and it takes it out into an abstract syntax tree. This is what I've tried to represent with my diagram. I'm not really going to talk about that middle section too much because it's a little bit in the weeds, but basically we're going from JavaScript into this node system, and then finally we build our abstract syntax tree. So what does this look like? Let's come back to our simple program. We have a fetch, a then, a catch, and we do a promise. So let's parse it out. There's a lot more to parsing JavaScript or building out a AST, but I focused it on the particular promise that or the particular function that we're interested in. So as you'll see, we have a lot of big words here, but we have this proxy, unallocated, blah, 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 fetch. Don't need to worry about it. That just means we're going to call a function fetch, and we're passing in a literal of my printf.cloud/logo.png. And then we have our then and our catch. The same ones that we're used to. They're just built in here, and we call this function literal, and something happens that we're going to kind of explore and take it further down into what the bytecode's going to look like. But again, it's still the same. We still have this promise. We still do this fetch. We still have a then. We still have a catch. So now we need to talk about how this relates to ignition and bytecode. So ignition is our bytecode builder. It takes an AST and it builds out the bytecode for us. And bytecode is really just a special instruction set. Computers only talk in a particular instruction set, often represented in assembly. And so bytecode is a way to bridge that gap from source code to kind of this lower level assembly. So what happens is we've moved past this AST now, and we're onto this rocket ship into this bytecode. So the bytecode generator is going to walk this AST, and it's going to generate bytecode for each of the things that we care about. And so what does this end up looking like? We're back to our regular promise. We have our then, our catch, and we're moving from AST to bytecode. I'm not going to show that exact transition. I'm just going to jump straight into what the bytecode's going to look like. That did not render well. Well, that's on me for using too small a text. Well, there's a bunch of functions in here. It's hard to tell, but down here we have our fetch of a logo, we have our then, and we have our catch. And then we have kind of the definition of our function that we're going to be executing and how it's going to tell the underlying JavaScript VM of what it needs to do and how it needs to behave. This is how a lot of just-in-time compilers are represented. Java, the JVM deals in bytecode as well. So in general, this is how VMs are going to effectively run. But we can't just stop at bytecode. We have to move now from V8 bytecode into libuv town. So libuv is really, for all intents and purposes, it's the event loop. This is the thing that we pull into Node and we say, here's how we execute this asynchronous I/O mechanism that we always talk about. Primarily designed for use in Node.js, but some other people use it too. The architecture of libuv is pretty straightforward. So we have network operations, we have file operations, and we have other operations. The OS independent, we have special things that we can do on particular OSs that don't really matter too much. We're doing a fetch, so we're really only concerned about the network and kind of this underlying operating system that we're going to get into. So what does the network architecture look like? Well, we got our normal usual suspects here. We got TCP, we got UDP, we got polling, pipes, streams, this general I/O that's happening. Basically, what we're doing is we're saying, hey, we have this HTTPS request. All HTTPS requests are represented in eventually TCP streams. So let's break it down into its constituent components. We may have some use for UDP operations, but I don't think they pop up too often in Node. So we kind of know the high-level architecture. We know how the networking kind of gets broken down. So how does the event loop get broken down? So this is the central part of libuv's functionality. This is where we do our polling for I/O, our scheduling of callbacks, our close handlers, set timeout, set immediate, all the things that we know and love. And all this is based on different sources of events. So we're going to take that event loop diagram that I had talked about and kind of expand it into its constituent components. So in general, this is on the left is how libuv is represented in C code, if you're very interested in C code. But we have 4 phases here for the 4 phases of the Node event loop. Libuv itself has 7 phases, but we're only interested in 4 phases because these 4 phases are actually defined in Node.js. So kind of this extra group here of queues are just the things that we don't care about. In general, we care about I/O poll, we We care about our timer heap, we care about closing handlers, and we care about checks. Check is set immediate. Timer heap is set timeout. IO polls, everything else. Close handlers, that's when you exit the program. That's when it crashes and panics on you and everything explodes. We're not going to explore too much on the set immediate and set timeout. Those have been covered very well in other places. We're going to focus really on just this IO mechanism and how epoll interacts. Cool. But in order to understand how epoll interacts, we have to go from libuvtown into the system mountain. I'm sure you've all heard this phrase on Unix, everything is a file. And if something's not a file, it's a process. Really, everything truly is a file. It's file descriptors all the way down. And so in order to understand what a file descriptor is, we kind of have to start with a general definition, which is nice because we kind of see that, okay, it's used to access a file or IO resource, such as pipe or network socket. And when you really think about it, you got files and you got network sockets. That's pretty much everything I need. Like, there's not much else that isn't a file descriptor. The only thing else left is really a process. So file descriptors are fairly complicated. This is going to be a high-level overview of how we get from a file descriptor to an actual file on your operating system. So it's a process unique identifier for a particular file or other IO resource. They have a bunch of integers here, non-negative integers, and negatives are kind of useless. They're reserved for error conditions. File descriptors are part of the POSIX API, and they are unique to a particular process. So we have kind of this next journey that we need to make, which is how do we get from file descriptors to this special inode table, which is our actual files here. We have to go through this intermediary called a file table. So I'm sure a lot of you have dealt with Linux, and you have this change mod 777644A plus W. What this is saying is it's modifying the file table to tell that file descriptor to point to a different potential access mechanism when it points to an inode table. So we're kind of recording how file descriptors were opened. 0 was opened with a read, 2 was opened with a read, 1 and various other ones were opened with potentially a read plus write. And that links back to our final thing, which is our inode table. This is describing a file system or a directory. These are going to store attributes of the block, things like metadata, like last change. When you do your LSA, this is kind of where you're finding all that information. And so we have, and as an example, 0, our file descriptor for our process, has a read of home/foo/bar. So file descriptors are kind of the base of Linux, and epoll is going to be the base of libuv. This is where we take it from file descriptor all the way up through the file system through epoll back to libuv. So this is an IO event notification system. We're going to talk a little bit about what this ends up looking like and how these things interact. So we have our same file descriptor table, our open file table, and our inode table here that we have already talked about. So we start out by creating epoll. We give it a size, and this size is how many file descriptors do we want to watch. We create it. This gets a kernel data structure. Note the process A kernel file system. So we have our kernel data structure now, and we have a file descriptor that's actually pointing to it. And we say, hey, for our process, epoll has a file descriptor that we're interested in. That points to some special thing in the kernel that we're interested in. Again, everything in Unix is a file. So now we need to add events to this thing. So we need to control the event notification mechanism. And to do this, we basically are passing in file descriptors to epoll for it to watch. We tell it what's the file descriptor identifier? What is the operation we want to perform on it? And what are some events that we're particularly interested in? We don't need to go through each one of these, but in general, what this ends up looking like is, boom, we've added, 6 files, descriptors to epoll that we want to monitor. So we've taken it now from, okay, we have JavaScript, we did a fetch, we have some callbacks that we want to execute. That got compiled into an AST, then to bytecode, then it went through an event loop. Now we're notifying on file descriptors, which are our network sockets. This is where we're interacting with printf.cloud/logo.png. And so we need to now figure out, how do we go from watching all this stuff to actually getting the data back? Well, we're coming back from system to libuv. And so this is where we get to talk about the thing that no one knows, triggers. So this is, there's 2 types of triggers. There's level triggers and there's event triggers. A level triggered event is really the easier to understand, and it's the way that epoll normally operates. We say, we're going to put a level, and once that file descriptor gets so much data, we will trigger an event. And so what does this look like? We have our file descriptor here. We're going to start with a small amount of data in the buffer at a predefined level. Maybe we've just sent the headers over. We haven't actually fully pulled the image yet, so we're just starting with a little bit. Okay, so we've added probably half the image at this point, but we haven't quite resolved the entire image yet. We're still waiting. Now, we've broken through our level here, and we've resolved the entire image, and we've said, hey, this is the point that we want to start returning data. And now we're going to tell the process, hey, stop what you're doing, listen to me, read this file descriptor, please. So we've read some of it, but not enough. So what's going to happen again is we read, and then we tell the process again, we say, hey, you haven't finished. Like, keep reading this until it gets below this level. And so now we've read most of it. Whatever's left is probably not important, and we've decided that we don't really care about it based on the level that we preemptively set. So what does this look like? Now we have this epoll wait. So this is the thing that says, hey, wait for events. Tell me what's going on with the file descriptors that I gave to you. We have a bunch of commands here. We have epoll.fd, which is the file descriptor for epoll, a structure of events that we're interested in populating once the event returns, a max number of events, and then a timeout to wait. In general, the timeout is some finite value. If it's 0, basically means wait forever. So typically, we don't want to wait forever, so we pass in some value of timeout. And so in this example, we've got 3 file descriptors that are ready, and we've returned them back to the process. We got these ones highlighted in yellow, and we said, hey, we populated your event data. Here's all the network traffic that you were interested in. And so now we can take that from libuv for that epoll and bring it back to V8. So now we can talk about how libuv is going to take this stuff from epoll and kind of distribute it to the system. So we have this timeout time for epoll wait. It's based on special timeout mechanisms within the Node.js or the libuv event loop. We have a watcher queue that we're looping through, trying to find events that we're particularly interested in. We have this number of file descriptors that gets returned from epoll wait that we're interested in adding to our watched loop and for telling systems that we have actually pulled event data from that. Once the timeout runs out, we return. We basically just read all the events, and once the events are read, we pass them back. It's a common misconception about asynchronous I/O or non-blocking event loop is this actually does block. It blocks for the timeout. Node.js is single-threaded. It gets a short timeout, but it does block at some point. As we all know, most computers are synchronous, and they kind of interact in very normal ways, and there's not some magic asynchronous file system that we can rely on. So we're going to loop through the watcher queue, add the associated events to the descriptor, wait on file descriptors if any events occurred, and pass the events back. So we're retrieving new I/O, and now, once we've gotten that data back, we can execute our callbacks. Remember our then and our catch. This is where we can say, hey, we've gotten our data back. Now we need to execute our then and a catch. So now we get to talk about the last little piece here that is key to this whole thing. There's this special little queue right in the middle here that executes promises. Everything else runs in this kind of macro state, but the promises have particular callbacks on this queue. So this is what we call the promise microtransaction queue. So we have macro phases, set timeout, set immediate, closing, I/O polling, and then we have our await and promises. What this is doing is it's scheduling these callbacks of saying, hey, there's I/O polling going on. I know there's I/O polling going on, but when they're done, put it in this transaction queue. And the reason this is done is because macro ticks can take a long time, and what the microtransaction queue is special, it gets to run after every single tick. So after every single tick, we go through the callbacks in the microtransaction queue and execute them. And this is where we get to take it from, we've read off a file descriptor, we've gotten all that PNG data back, and now we get to execute our then and our catch. This is where we're running them. So to wrap up, and I know that was a lot, we have an overview of Node.js. We've talked about all these pieces here, kind of how it goes from JavaScript to an abstract syntax tree, through the bytecode, into the event loop, where we have our special polling mechanism and microtransaction queue, how that polling mechanism is actually file descriptors at the end of the day with these level-triggered interrupts that eventually come back to this promise microtransaction queue and come all the way back to JavaScript. So from JavaScript to bytecode, we take JavaScript down to bytecode, we parse it into an abstract syntax tree, and pass it through a compiler called Ignition, which produces something for the Node.js virtual machine. We take that bytecode and we execute it by passing it to libuv's event loop for execution. We're going through 4 major phases of the event loop and passing callbacks onto a queue that are eventually going to be processed by the underlying operating system. Those callbacks pass the epoll to be handled via file descriptors, and then eventually get notified via event triggers in order to inform us when an event like a network request completes. We poll epoll periodically throughout the duration of the event loop to find completed events like network requests. And once they're complete, we can read the data and pass it on to the callback function for execution. And finally, we finish by resolving the promise on the microtransaction queue, which schedules the callbacks like then and catch to finally finish our promise execution. And I know that was a lot, so questions?
Thank you so much for the talk.
Yeah.
I think some of the nomenclature might be tripping me up. So in the initial JavaScript example where you show a promise being resolved, you have the promise and then it runs a .then to resolve the promise. But then you also mentioned interrupts once we go past the trigger level. So is the .then resolving the promise? Is the interrupt just bringing it about, or is there a combination of the two? I think that's tripping me up a little bit.
So the .then is going to be executed after the promise resolves. That's a callback that says, like, we've done this, now do this. That's kind of the idea behind then. So we do promise, then something else. So in this case, we had a log statement that said promise resolved. Because we didn't really do anything with the image data, we just wanted to know when it was done, right? So that was the whole idea there behind the dot then. It's after the promise resolution, and it's a callback that gets executed as part of the overall promise resolution process. Does that make sense?
And the dot interrupt part? I mean, sorry, the interrupt, oh, sorry. And the interrupt caused by going over the trigger level, how does that play into the resolve of the promise?
Yeah, so we have our fetch, which creates a file descriptor, goes to a network socket, and that interrupt is basically saying, hey, we're done. We have actually finished, and so now we can bring it all the way back and resolve that promise. The dot then is going to be separate from that interrupt. So we go through that whole process of resolving, and then we bring it back to JavaScript code to say, okay, now we've resolved the promise. We had our interrupt that said, we're done reading all this data from the network. Now we can execute some normal JavaScript code like a console log. Sorry. Does that make sense?
Yes, thank you.
Cool.
I was just curious, in your journey into the transformation of bytecode, is there any practical or important difference between promise.then.catch versus async await, or does it kind of functionally compile down to the same thing?
So there is a important difference. It's very minute and kind of in the weeds. Async await has better stack traces for error handling than promise.then or catch. That is really the main difference. Anything beyond that is going to be semantics around how a particular underlying system executes that promise chain. So, cool.
Yeah, so you mentioned in the event loop that the system is constantly checking occasionally that a promise is being resolved.
Yep.
Rather than the promise interrupting it some magical way. Okay.
Yep.
Very cool.
Yeah. So there's ticks. They're called ticks for the event loop, and basically a tick is one full iteration through the cycle. So it goes through everything every time, and then eventually asks what's ready.
I know this talk was focused mostly Node.js and libuv talking to Linux systems. I'm curious if you can speak at a high level about the distinctions of running the event loop in the browser, kind of where that goes, and maybe even non-Linux systems like Windows. Is it a similar path and just different libraries? Or?
Yeah, so V8's gonna run in the browser. Beyond that, I don't actually know. I don't know how it gets from V8 out to the network. File descriptors, Linux, that's my bread and butter. So as soon as I get into how the particulars of a browser opens a network request, I'm not entirely sure.
What got you so interested in promises? Was it general curiosity about the stuff you're working with every day, or was there a particular situation that got you digging deeper?
So this was probably the combination of 6 or 7 talks that I had given at a previous company as a part of introducing junior and mid-level engineers into Node.js and kind of how it executed. And so each one of these pieces were broken down into individual pieces. And I ran into this at my new company, Cloudflare, we're hiring. And my team had basically asked for a abridged version, which this is the attempt for them. So that was the focus here. In general, promises are kind of syntactic sugar on the general Node.js concepts. So it was easy to append them on as kind of the main thing that people interact with on their day-to-day. Sweet. I think we got one more up here.
I may have been mistaken, but when you showed us the C code for V8, it looked like the order of method execution was catch, then?
Yeah, so that's actually just a definition of it.
Okay.
So it's not in the particular order that it would actually be executed. It was more just here's a general class template of what a promise is going to look like.
Okay.
Does that make sense?
It does make sense. I always figured that maybe the design could have been different where the catch was first, therefore requiring error handling up front as opposed to following with then, and if you would see that changing in design in the future at all.
So that is the main thing about async await. That's what significantly changed the error stack traces, is that kind of top level catch behavior. So yeah.
Take a step way back.
Yep.
What's a promise?
So really a promise is kind of this, we used to be stuck in this callback hell, as some people might remember, where we're stuck like executing a callback, which passed the callback and so on and so forth. And so promises came along and they said, we had this asynchronous event loop which ran these macro tasks and they were just executing callbacks. And we wanted to flatten that chain. So we said, let's take a promise, which is this syntactic sugar around callbacks, and we'll flatten everything and we'll say, hey, you can just start returning this code that represents a set of callbacks instead of how we used to execute them before. So really it's just a means of saying something I don't know when it's going to happen is in this JavaScript code, and whenever it does finish, I want you to do something else after. Does that make sense? Yeah. Cool.
All right, thank you so much, Mikey.
Yeah.
And thank you everyone for joining us tonight. It looks like there's still a bit of food back there if you want a bit more to eat. Have a safe trip back home, and we'll see you in a month.
So in a month, we're doing lightning talks. So if you have a lightning talk that you'd like to give, DenverScript.com has a link to the talk submission. So we'd love to see some submissions. And I'll give you the exact date of the next meetup. It will be Tuesday, September 26th, lightning talks. So please submit. Thank you. Check. We have stickers up here if you'd like some stickers, so definitely grab a sticker before you go.